Okay, that's time. So just turn in what you have. Don't freak out too much if you didn't get to the end. So here's the way I'm going to do this. Anyone else? Last call, last call. So the way I'm going to do this is that as far as the 10-point bonus, I'm going to grade this and see how many points I will add to your exam. In terms of the quiz grade, the minimum score you can get is a 70. Okay, so it's almost like a participation grade, but if you get things right, you can get up to 100. All right, so does that make sense? Yes? Okay. All right, so what I'm going to do is I'll get these graded, and then what I do is I cut the top off and I turn it into the department. And then they don't know whose is whose, and they mix up all the classes, and then they take a random sample, and they just kind of evaluate like where we are. Like, does that make sense? Okay. I don't remember what the answer was. What did y'all get for the answer? 19? 219 for the, yeah, okay, so sounds right. Okay, so this is it. We're down to our last 2 lectures. Yes? Should have. Did it not show up? Really? Okay. When did you check?
I just checked like an hour ago.
Double check. Double check after class. If for some reason it's not there, just let me know. Okay? All right. So this is our last. We have today, and then we have Thursday. That's it. And then we have our final is next week. Is it on Thursday? Yeah, it's on Thursday. So we'll talk more about that later. So make sure you're here the next 2 classes, all right? So what I thought I would do here is kind of give you some idea of where you're headed. How many people have to take Cal 2? Okay. Anyone need Cal 3? You think maybe? Okay, only a few. So this might be a question mark for some of you. I want to at least get you introduced to the ideas here so that you have some idea of what's going on. But I thought we'd start by just reviewing the things in Cal 1. So of course we started the class, the idea, everything in calculus, all of these, everything, Cal 1, 2, 3, all of them depend on the idea of the limit. Everything is based on the limit. So if you were to look at all the calculus topics, right in the center would be the limit, and then everything branches out from that, okay? So the limit is what we started with, and that wasn't that fun. And then we defined the derivative, and then I gave you a bunch of rules, you know, power rule, product rule, quotient rule, chain rule, and you try and get good at those. Then we also talked about implicit differentiation. That's when you can't solve for y, so you have to like take the derivative of both sides, and we did that. We did L'Hopital's rule, and I actually have some news for you on L'Hopital's rule. I actually looked into this over the weekend, and I was shocked. I'm like beside myself. I've always respected L'Hopital for his rule. You know, I even like sing my little L'Hopital chant. I'm gonna have to change it. I'm gonna have to change my chant. I'm gonna actually have to start like chanting Bernoulli, because what happened was, I don't know why I can't talk today. L'Hopital was helping finance Bernoulli in his research, and he said, you know, whatever you figure out, I get to put my name on it. So he basically paid for it, if that makes sense. So L'Hopital was a mathematician as far as I could tell, but there's some debate about it, but I'm going to look into it a little more, but L'Hopital may not be the one who came up with the rule. So Bernoulli, you've heard of the Bernoulli equations, and you've heard of Bernoulli? Scientist, physicist? Okay, well, anyways. All right, so move on. So then we did related rates. That's, you know, the ladder slides down the wall, the spherical balloon is being inflated, the plane flies overhead, word problems, right? Then we did the derivative and how it affects the shape of a graph. So, you know, increasing, decreasing, concave, up, down, inflection points, all that stuff. Then we did some curve sketching, and then we did optimization, which are word problems having to do with this idea of up, down, and stuff like that. So there's a lot of smaller things within here that we discussed, but these are the main ones. But if you were to just like sit a Cal 1 student down and like ask them to summarize what's Cal 1 in like one simple idea, I think this is it right here. In Cal 1, what we do is we take a function, functions that we've studied in algebra and pre-cal, and we say, hey, if we go to a point on that function, can I find the slope of the tangent line? And the answer is yes. You have to take the derivative of the function at that point, and that will give you the slope of the line, right? So that's it kind of in a nutshell. So let me explain to you kind of in a nutshell. I'm not going to go through topic by topic what Cal 2 is. I'm going to try and give you like more of a visual idea of what you do in Cal 2. So the first thing you do is you say, all right, let's say we have this function, but instead of letting it just go on forever in both directions, let's define it on a closed interval between A and let's say B. So this is like, in this class, I could do this for you and I could ask you to find the absolute maximum and minimum, right? So long as this is a continuous function, you should be able to find the absolute maximum using the closed interval method, right? So in Cal 2, we do something completely crazy different from this. What we do is we say, look, if you were to imagine dropping straight down from these points and taking a look at this region right here between that function and the x-axis, the question is, can you find the area of that region? All right? That's the fundamental first question that we have in Cal 2. Finding the area below a function. And we find a way to do it. And then we say, all right, let's go a little further. How about if we have two functions, f and g, can we find the area between the two functions? Like this right here. Can you find that? All right? And so we do that, we figure it out, and then we say, okay, let's do something even crazier. Imagine that I take this region, okay? Take this entire graph, imagine that I pull it out into three-dimensional space. All right, you see it here? Then I want you to take that region right there. Here's the x-axis. I'd like for you to imagine taking that and wrapping it around the x-axis. Okay, so it swings through around the x-axis, and it creates a solid. Almost like a donut. Can you all visualize that? So wrap this thing around the x-axis, and you get, now I'll try and draw a little picture of this. It's not going to be that great, but I'll do my best. Okay, that's terrible, but you get the idea. That thing's wrapped around the x-axis. That's horrible. The question now would be, what's the volume of that? Because now it's three-dimensional solid. So what is the volume? Let me give you an easier example. What if I were to take this graph right here, this little line segment that goes from here to here, and take that area underneath it. And if I ask you to wrap that around the x-axis, it would look like this. And that would be a cone, wouldn't it? Like sideways. Do y'all see that thing wrapped around, creating that? Your x-axis is like going through there like that. So what is the volume of that? That's the question. Okay, can we find it? Now, what if I took this thing and instead of wrapping around the x-axis, I asked you to wrap it around the y-axis? Would you get the same solid? No. What would be the difference between this around here or this around the y-axis? You'd have a hole in the middle, right? You would look more like this. Do y'all see that? That's this wrapped around here. So like I could actually put this marker into that hole. Here there's no hole, right? It's solid all the way through. These will have two different volumes. So we ask, what's the volume of that? A very interesting problem in Cal 2 that you can't do right away, you have to get pretty far into the class to do it, is let's say I take a quarter of a circle like that, okay? And I ask you to wrap it around the x-axis. What would you get? You get half a ball, wouldn't you? And if I ask you for the volume of this, then you actually have come up with a formula for the volume of half of a sphere, or half of a ball. And then you could just double that answer, and that's how you can generate the formula that you read in the book, 4/3 pi r cubed. That formula, we can actually get it in Cal 2, we can create it ourselves. If that makes sense. Yes?
So basically it's just a lot of geometry.
Well, there's a lot of visual, in Cal 2 there are a lot of things that are visual that kind of help you to kind of see what you're doing. So all that kind of makes sense? All right, so now, after we do that, the next thing we do is we say, all right, let's go back and take a look at this function again. And this is something we've never actually thought about in here. Let's take our function, let's make it really wavy, and let's put it right here like that. Okay? So up to this point, we can find the slope of the tangent line at any point, right? We can find the area underneath that. We can wrap it around the x-axis or the y-axis and find the volumes, right? But what if I take this thing, this function, take it off the page, just the function, and imagine it's like a string, and straighten it out and measure how long it is. Does that make sense? That's called the arc length. So what would the length of this thing be? And believe it or not, that's not easy. Well, yeah, it probably seems like that'd be hard, right? Yeah. What is the length of that? It turns out that in general is not an easy thing to do. That we have to pick very special functions. That way you can do them. If we just grab a random function, most likely you can't do it. Now we could use a computer to do it, but by hand it might be really tough. Okay, another problem that we do, we go back to this idea. Let me go back to this one. Now I told you we could wrap that around the x-axis, right? And we would get this. And we said, let's find the volume of that. A different question would be, what's the surface area of it? So that would be, if you were trying to paint the outside of it, like how much area would that be? That's different from volume, right? And it turns out that that's also very challenging, but we can do it. So surface area. Okay? All right. To do everything I've explained up here, to do all of these things that I've explained, you have to be able to find what's called antiderivatives of functions. So we have been spending our time in this class finding the derivative, which means we start with the function, we take its derivative, we get something, right? In Cal 2, we're going to start with the function, but we have to go backwards. We have to say, hey, look, see this function? It's the derivative of something. Go figure out what it's the derivative of. Like, for example, if I gave you the function 2x, can you tell me what, that's not 2x, I just gave you the answer, damn it. Oh well. That's a function. Can you tell me, that's the derivative of what function? X squared, right? So the antiderivative of this function is x squared. Do y'all see that? Okay. So all of these things that I showed you here, all these visual things, before we even start that, we have to spend like 5 weeks figuring out how to find antiderivatives of functions, because you can't do this until you can find antiderivatives. And so there are different techniques to find antiderivatives. You know how we had the rules here? You know how we had the rules? And not to insult anyone here, but you can kind of teach a monkey these rules in the terms of there's a process, right? There's a procedure. Like the power rule is very specific. Power comes down, subtract 1, right? Product rule, derivative first times second plus derivative second times first. Very, very clean. Quotient rule, same thing. There's a rule. Chain rule is complicated, but there is a process. When you're going backwards, when you're trying to go from here backwards, you will never get a set of rules. You will get procedures. No. You will get techniques of integration is what they're called. And they are basically like, you have to look at the problem and you have to figure out like which technique do you think you want to use, and you might pick the wrong one. And you might have to crumble it up and start over. And you're going to fail many more times than you're going to succeed. And so it's a much more difficult class because there's this sort of intuition you have to have about how to go backwards, but it is directly related to how comfortable you are going forward. So if you're struggling with these rules this way, going backwards is exponentially more difficult. So we spend the first few weeks teaching you these techniques of integration or techniques of finding antiderivatives. The first one's called U substitution, which I'm going to show you Thursday. Okay, and then you go U substitution, integration by parts, trig integrals, trigonometric substitutions, partial fraction decomposition. Those are the techniques. And then once you have those, you hope it's enough. All right, you hope you can do it. So we teach you how to try and do antiderivatives. Then you can do all this. All right, and then we say, all right, done. Then we start chapter 8. Chapter 8 in this book is what's called sequences in series. So chapter 8 to me is the monster in Cal 2. Okay, sequences in series. And the reason why it's the monster is because by the time you get to it, you're exhausted. Okay, because Cal 2 will test your sanity. All right, so you get to sequences in series and you're tired. It's the last 6 weeks of the class maybe, right? You get to that, and then it's something that you have not done before. Like, I'm pretty sure nobody in here has done sequences in series. And I can't really explain what it is too much other than to maybe show you an example that might help. Have I shown y'all what e to the x is? Like, I think I showed you a limit, right? But I never did this, did I? Okay, so you see you start e to the x is 1 plus x squared over 2 plus x cubed over 2 times 3 plus x to the 4th over 2 times 3 times 4. What's the next one? X to the 5th over 2 times 3 times 4 times 5. And if you've ever learned this before, that's really 5, what we call factorial. Don't worry about it. Okay, so, and this actually keeps going forever. It never stops, this pattern. So this part right here is called the Maclaurin series, or the power series expansion of e to the x. I know that looks strange, but every function that you've ever dealt with in your life can be expanded out into what is called its power series. And this is what a computer looks at. A computer has no idea what e to the x is. This is what your computer thinks e to the x is. Those of you who were here that day that you didn't have to be here, we talked about the Newtons, and we were talking about how the computer can only do add and subtract in powers. Like, the computer can do that. The computer has no idea what that is. So I want you to see something about this. What's the derivative of e to the x? Itself, right? Let's see if that works here. What if I ask you to take derivative of this? What's derivative of 1? 0. What's derivative of x? 1. Plus, okay, what's derivative of x squared over 2? So the 2 comes out, right? Cancels with that 2, and you're left with what? Just x. Plus, okay, derivative of this. 3 comes out, cancels with the 3, but there's still a 2 there. And then what's up here? X squared over 2, right? Next one, 4 comes out, cancels with this 4. You're left with an x cubed over what? The 2 times 3 is still there, right? And I can keep doing this. Do you see that these two are exactly the same? Right? 1, 1, x, 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 right? This shows you how e to the x is its own derivative. So sequences is a series. It's such a huge topic, I can't show you one thing and one thing only. What I can tell you is that if you don't have sequences in series, then you can be given a problem and be asked to find the antiderivative, and you can get stuck. Like, if you try those techniques I told you, substitution, integration by parts, you try those techniques and you can't do it, then if you don't have this, you're done. Like, you're dead in the water. But if you have this, you can actually still do antiderivatives. Here's one last thing on this, because I don't want to eat up too much more time. Still talking about sequences in series. Just out of curiosity, imagine that I have a container That holds exactly 1 cup. All right? That's exactly 1 cup. And what I'm going to do is I'm going to get a container with water. This is empty right now, okay? I'm going to get a container with water. I'm going to pour in 1/10 of a cup. Okay, so I poured it in there. There's the water level. You see it there? Okay? And then I'm going to go and pour in after that 1/100th of a cup. And then I'm going to do 1/1000th of a cup. And then I'm going to do 1/10,000th of a cup, right? And I'm going to keep doing this forever. Does the cup overfill? What do you think? No? I'm seeing no's and yeses, so who's brave? Who wants to give me what they think and defend your logic or your reasoning behind it? And don't worry, I'm not going to make you feel bad if you're wrong, because this is the reason I'm giving it to you is because you can argue both ways and you have pretty good arguments both ways. So, no brave soul? Okay, what? The amounts are getting smaller and smaller. So what you're thinking, it will or will not? It will not overfill? Okay. And you're saying it will overfill. So do you want to argue against why?
Because even though you're adding a small amount, eventually that small amount is going to equal a large amount and it's going to come over.
So she's saying you're still adding small amounts, so it's going to overfill.
Yeah, but we're approaching infinity.
What's approaching infinity?
The amount that we're putting in.
It's infinitesimally small,
Yes.
right? These are headed to 0, right?
Yes, we're never going to ever.
Is it evaporating?
No, okay, so this is this is a good question. We are going to neglect evaporation and all that. This is purely theoretical. Okay, this is a perfect container with a perfect, I mean, I can't measure, at some point you can't measure that precise, right? So in theory though, like what happens here? So you're saying the amounts are getting smaller, and so it won't, at some point it doesn't impact the, I don't know, I'm having trouble with that. You're saying that
Even though you're adding a tiny amount, eventually all of that added together is
it's going to eventually overflow. So let me challenge your argument, okay? I'm going to try and refine what you're saying. Does everyone agree that this is a positive number? Okay, is that a positive number? Is that a positive number? Are all of these positive numbers? Am I adding them together? How many of them am I adding? An infinite number of them. So to try and argue against you, I'm going to say you're telling me that if I have a finite container and I keep adding something, right? Something. Each one of these is something. Even though they're small, it's something. You're telling me that it's like not going to overfill?
Yes, it would. But no, I don't think it would. I don't think it would.
Okay, so it will not overfill.
Yeah, it would keep just getting smaller and smaller as we approach the limit.
Okay, so let me, the answer is that it will not overfill, and I'll show you why in a second. But let me, okay, so what about this? No, let's do this one. So your argument is that these are getting smaller and smaller, so it won't overfill. These are also getting smaller and smaller.
Yes.
So same thing, it won't overfill?
Better, greater quantities.
So these are bigger than these? So you're telling me now that it matters like how fast they're getting small? Exactly, that is exactly correct. Look, do you agree these amounts are getting smaller and smaller? If I do this, it will overfill. If I do this, it won't. The reason I know that is because I understand what's going on here, okay? But from your spectator view, if your argument is that they get smaller and that's why they won't overfill, it's about how fast they're getting small. Okay, so this is what we call a harmonic series, and this is what we call a geometric series. All harmonic series diverge, which means that they all overfill. They all become infinitely big. Geometric series converge to a number so long as certain conditions are met, but this one meets the conditions, This one converges. And I can tell you what it converges to. It's kind of crazy because this one, it's not going to fill up the cup. It's not even going to fill up half the cup. And I'll show you how I can justify it. I'm just going to convert all these to decimals. So 1/10 is 0.1. 1/100th is 0.01. 0.001 is the next one. Next one's 0.0001. And if I start adding these up forever, what do I get? 0.111 repeated forever, which is exactly 1/9. Okay? So if you go,
Started with 1/10, that's 1/9. That's it.
1/10 is smaller than 1/9.
Yeah, but that's all you go up by?
That's it. Yeah. So this is, if you could keep doing this forever, okay, if you could keep pouring the way I said to pour, not only will you not overfill the cup, you won't fill it up halfway, you will fill it up, well, this is where things get weird, 1/9 of the way, but that means you'd have to do it forever. If you ever stop, you're going to be a little short of 1/9. A little bit short. Make sense? It's weird, right? It's weird. Well, so is chapter 8. Chapter 8 is weird. So, all right. Cal 3, take everything we've done, take it into three-dimensional space, throw vector fields in, and do all the calculus again. So you basically do both differential and integral calculus in higher dimensional space, but you are also using vector functions instead of scalar functions. This is a scalar function. You have to learn about vector functions, and yeah, this class is not necessarily any harder than these two. I just think this is a very dense class. It's like packed very tight. So is Cal 2. Cal 2 is super dense. It's a marathon you have to sprint. Yes?
I was just going to ask, so, I mean, obviously there's going to be a lot more you learn in the class, but like, from a I guess, academic view, like, useful that I could use in real life, some of the like things that really interested me was like when we did optimization. Because you kind of have to use what you know before and then use it and use it for real life problems. Is there
Yes.
anything like that in Cal 2?
Yes.
Like, sensory ability to do that?
So you know how that area that we were looking at, I said we could find the area? That can be used, it just depends on the framework with which the problem is placed. So that area could wind up representing the total work done moving an object from one point to another. So like, you know, you're applying a force to some object, moving it, and you'd like to know how much work was done moving it from there to there. Well, it's the area under some curve, all right? Or if you have like a dam holding water back and you want to know the hydrostatic pressure, so you want to know the pressure at different levels, you can use antiderivatives to do that. There's a lot of different applications. In a Cal 2 class, we don't do a lot of applications because we let you go to physics, and then when there's like, okay, we just need to find the area under this curve, you're like, oh, okay, I know how to do that. Another one is if you have an object, you can find its center of mass. So if I gave you some weird shaped object, some non-weird, just some, you know, if I give you like a circle, if I give you a sphere, then the center of mass is in the center. But if I give you something that's uniform, then can you find the center of mass? And the answer is yes, you can. You can find the center of mass of these things. You have to do antiderivatives to do it though. So I don't know if that helps, but yeah? Okay. Yeah. All right. What's that?
Can I ask?
Yeah, go ahead.
Differential equations.
Differential equations, yeah?
And then you have
So differential equations is going to be you trying to solve equations. Like if I ask you to solve this equation, obviously that is easy to solve, right? Okay, so x is 4 there. So your answer is a number, right? Okay, so what if I ask you to solve this equation? Then what I'm asking you is to find me a function. Find me a function of x such that when I take the derivative of it, it's the same as the original function. So what would qualify here? E to the x would be a solution to this equation, right? E to the x would be a solution to this equation. In fact, if I change that to double prime like that, e to the x would still be a solution to that equation. So then you get more complicated. Like, what if you have 2y times x minus y prime equals 0? Now, find me the function that when I take twice the function, multiply it times x, and then subtract its own derivative, I get 0. Find the function. Welcome to differential equations. That's what it is. You're trying to solve an equation, but your solution is a function. Okay? And it involves, your equation involves derivatives. So the equation involves derivatives. Derivatives are like differential calculus, differential equations. Does that make sense? Any equation that has a function and its own derivative in it is called a differential equation. I'm thinking about doing it soon. Right now I'm actually currently working on getting all the solutions for the homework done. So I'm working on that part first. Once I get that done, then I'll offer it. So not anytime soon. Not anytime soon. Okay. All right, that's it. Oh, linear algebra, yeah, we won't get into linear algebra right now. All right, so you're ready to start to transition into Cal 2 a little bit here? Okay. So we're going to start this with I don't want you all to feel like you should be scared of Calculus 2. You should just be ready, okay? Because it is no. I think Cal 2 is the class that will test whether or not you really, really want to be an engineer or really, really want to be a computer science major. Cal 2 will be that class. All right? But when you get through it, your idea of what's hard will change. So like you'll look back at Cal 1 and you'll wish that you were doing that again. Like, you know what I'm saying? You'll be like, wow, that stuff. Okay, so here we go. This is just some definitions. A function capital F is called an antiderivative. Look at that word right there. A function capital F is called an antiderivative of little f on the interval I if the derivative of capital F is equal to little f for all x in the interval. Now look at that word I underline. A function capital F is called an antiderivative. I did not put the antiderivative, did I? The would imply that there's only one answer. When I say and, it means that possibly there's more than one answer. So I want to try and illustrate this idea with an example here on the side. Let's say that I define capital F of x to be equal to x squared. And then I tell you that little f of x is equal to 2x. Do we all agree that this is an antiderivative of this? Do we agree with that? How do you check it? It's a simple check. Take the derivative of that, you better get this, right? Okay, so if I take the derivative of the capital F and I get the little f, then I have found an antiderivative of little f, right? But that's not a unique answer. Can somebody give me another capital F that would have worked? Okay, so another candidate would have been f of x equals what? X squared plus 1 would have worked, wouldn't it? Because when you take derivative of this, you still get the 2x, but then the derivative of a constant is going to be 0. So you're still going to get 2x. So this is also an antiderivative of 2x. So already, right off the bat, we've learned something huge that's different than when we were in Cal 1. Well, we're still in Cal 1, but in Cal 1, when we take a derivative, right, we get a single function as an answer. We're already seeing that in Cal 2, if we have a function and we are trying to find an antiderivative, we are never going to get a single function. We are always going to get an infinite number of functions, because I could use any number here, right? I could have done plus 2, plus 3, plus 4, plus pi, minus 7, minus 10, minus e, anything I want, right? And this, all of them would have worked, because when I took the derivative, it would go back to 2x, right? So this is what this is saying. If f is an antiderivative of little f, then that function you found plus c is the most general antiderivative of f. Here c means any constant. So what we do is we try and account for the fact that we know that any number out here would work. So what I say is, okay, go back to this. What is the most general antiderivative of this we can find? Capital F of x would be 2x, not 2x, why am I writing 2x? X squared plus c. So we all understand that that c represents any number you want, all right? And that is called the general antiderivative of little f. So I have this same example down here. I have it in pictures for us so you can visualize what's happening. So 2x is the red one, right? The blue one is x squared, and I could actually have any value of c. So what would adding a number to that x squared do? It's either going to move it up, right, if I add a positive number, or it's going to move it down. Any of these functions would work, wouldn't they? Okay, so let's look at let's look at a family of them. So those are, let me give you less than that. There's a few of them, right? There's a few of the antiderivatives. I just picked some different values of c. I want you to notice what they all have in common. Where's my, I thought there was another adjustment on here. Is it not showing up? Oh, okay, here we go. There we go, that's what I wanted. Right there. Okay, so notice that if I were to go out to, let's say, 1 here, and go up to this top one, I'm going to have a slope of a tangent line, right? If I go out to 1, let me move to 1 because I'm not quite at 1. I think that's pretty close. If I go to 1 on this first one, I have a slope here. If I go to the second one, I have a slope. If I go to here, I have a slope. And do you see that all those slopes are the same? On any one of these parabolas, x squared plus any constant, up or down, at some value, they all have the same derivative, right? Which is why, no matter what this is, your derivative is always the same. And so there are an infinite number of them, right? There's an infinite number in there. And that's the best we can ever do, is to give an answer that gives you a family of functions. So here's just another example. The red one is the little f, and the blue one is the capital F, the antiderivative. And again, we can sit here and look at all of the family of them. And again, they all have the same property, that if you pick some point and go to that point on any of those functions, the slope of tangent line is the same the whole time. All right, so I just want you to see in that we get a family of functions as our answer. That's the main thing to take away from this. So what are some of our antiderivatives that we could probably come up with without anyone helping us right now? Like if I gave you little f right now, let's see if we can't come up with capital F's for some functions on our own here. So let me give you one. I'm going to start in what I think will be an order that you'll be able to process this the best. What is the antiderivative? So I want you to tell me what the general antiderivative of cosine would be, cosine x. Sine of x. Everyone agree? Plus some c, right? So right here, if you give me a sine x plus any number, if I take derivative of that, I'm going to get cosine x, right? Okay. I did that one intentionally before sine. So now I'm going to go to sine because I want to see if you understand there's something a little bit off on this one. Yeah, your capital F here, is not cosine, but what? Negative cosine of x. Now, do not confuse this, all right? Do not confuse this. I understand that the derivative of sine is cosine, but that's not what we're doing. We're saying, hey, here's sine. What is its antiderivative? So what do I have to take the derivative of to get sine? I can't just use cosine, because the derivative of cosine of x is negative sine x, right? So I have to put a negative in front so that the negative and negative come together to give me the positive sign. That makes sense? So that's our most general antiderivative for sine. All right? Let me give you another one that I think you can do right now. Secant squared x. Do you know what you take the derivative of to get secant squared x? Tangent x. Plus c. There are many math professors out there that will count your problem completely wrong if you don't put plus c. Okay, because it's not one of these things where you get a choice. That plus c has to be there because you're saying, look, I know it within a constant. I don't know exactly. There's not just one answer, right? So it's like if you leave the c out, you've left out an infinite number of answers. I'm kind of a little more laid back about that. Okay, so what you should be doing right now is just kind of running through your little Rolodex in your mind of the things you know how to take the derivatives of. So what are some other ones that we know? How about this one? We just did this one a second ago. So capital F of x should be e to the x plus c, right? Because we already know that the derivative of e to the x is itself. What about log? What about natural log? What should I put over here? 1 over x. 1 over x. Because I know that's the derivative of natural log of x. So my capital, absolute value. But I'm just going to put this for now. I mean, technically, well, I'll do it. We need to have absolute value here because can't plug negatives in, but don't worry too much about that. We know derivative of natural log of x is 1 over x, right? Any others that we know? Root x. Do we know the antiderivative of root x? Or you're saying root x on this side?
You could say put 1 over 2 squared.
1 over 2 root x over there, and we know that it would come from root x, yes? Okay.
Do a series of logs.
Maybe there's a lot of things we could put over here now, right? There's also a lot of things we can't. Like, for example, what if I put over here secant of x? Not secant squared, but secant. Did we ever take the derivative of something and get secant x? Never did. Never did, right? So right now, we don't know what it is, but would you like to know what it is? Okay, the antiderivative of this is the natural log of the absolute value of secant of x plus tangent of x plus c. All right? Nobody in here is going to look at that and give me that answer, okay? It's just not happening. So how in the world is the antiderivative of this, right? This seems so simple. That's just 1 over cosine x, right? That's all that is? That's all that is. What's the antiderivative of 1 over cosine x? There it is. Right? So I took that off of a table in the back of the book. But in your Cal 2 class, usually they'll let you use a very basic table that has a lot of these on here. And usually this one would be included. But let's just verify quickly. Let's verify quickly that this is correct. Let's verify it. What is the derivative of this? So first of all, we have natural log of something, right? So derivative of that is 1 over whatever's up here. Secant x plus tangent x, right? Times the derivative of what's inside, right? What's derivative of secant x? See, so at this point, you're in Cal 2 now. So your Cal 2 instructor expects that you know what the derivative of secant x is. It's secant x tangent x. And then you say plus derivative of tangent x, which your professor knows, is secant squared x, right? And then we're done. I took off on your quiz if you didn't put parentheses. Why are the parentheses so important? Because if they're not there, then technically you mean only this times this. That's all this right here is hanging out on its own. Okay, so, and I know some of you cleaned it up and got the right answer because you did it right, but notation-wise, that is incorrect without parentheses, all right? So it must be there. It's not important that you know what you're doing. It's important that the notation's correct. It's like leaving periods off sentences, all right? It's important. All right, so now, what can I do here? You could put all this on top of that, right? What should this turn out to be at the end of the day, though? It better be secant x. Do y'all see what I can do? What can I do? Yeah, see in here, I can take a secant out. So if I take a secant x out right there, I'm left with the tangent x plus a secant x, right? And then this and this cancel, and you get secant x. So indeed, it was a general antiderivative because we had plus c. So do you see that it's probably going to be pretty frickin' hard to go from here to that? Like, how do we get from here to that? Do y'all see that that's going to be a challenge? Okay? We're not going to touch it in this class, but in Cal 2 you will. Okay, so let's try something else. Let me give you some other stuff. How about this one? How about the antiderivative of x? What do you take the derivative of to get x? I'm not asking you what the derivative of x is, because that's 1, right? What do you take derivative of to get that? What do we know about taking the derivatives of x raised to powers? What happens to the power? When you take the derivative, the power comes out, right? And the power goes down by 1, right? That means whatever this antiderivative is, it needed to start out as x to what power? Now that's where it ended up. It ended up as a 1 here, right? So when I took the derivative, the power had to come down, and it came down to 1. So what did it start at? 2. So x squared is a pretty good candidate, but why won't this work? Because the 2 is going to come out, right? And then I would get 2x, and I don't want 2x, I want x. So maybe I should just be clever here and put a 1/2 in front of it. Now will it work? When the 2 comes out, it hits the 1/2, they go away, and you're left with just an x to the first power. Then I need to say plus c. Right? Yes?
Couldn't you say it like it would be 1 over n?
Okay, I'm leading to that. I'm trying to get to a general formula. I thought I would start with this and build to it. Yeah, so what would happen here? It's good if you see that, but I'm trying to build up to it. What about x squared? Look, you're not going to be wanting to look at this as in, I want to memorize everything, every antiderivative he puts on the board. Okay? You don't want to look at it that way. We're trying to get to some formulas here, all right, at this point. So what about x squared? Something similar, right? You know you're going to start with an x cubed, right? You know you're going to have a plus c, but you have to kill the 3, don't you? So to kill the 3, you come out here with the 1/3. Right? Make sense? So what about if this is x to the 3rd? Then you'll put what out here? 1/4 x to the 4th plus c. Does that make sense? Throw a little curveball at you. One what? What? 20x to the fourth plus c. Will that work? I'm going to write it down. Don't write it, though. Would that work? What happens? That 4 comes out, we're going to get 80, right? Right? So you're on the right track, but not quite. So let me ask you something real quick. When we're taking derivatives, the derivative of a constant is what? The derivative of a constant by itself is 0. But what if the constant is out in front of the function? What do we do with the constant when we're taking derivatives? It just comes along, doesn't it? Well, same thing happens when you go backwards. So if I have a constant in front of this, see this 5? I know the antiderivative, the 5 will come with me, okay? And then all I do is I focus my attention on this part, which is 1/4 x to the 4th from the previous line, right? Now, just slide the 5 on top, 5/4 x to the 4th plus c. And now if you check this, this will work. Because when the 4 comes out, what happens? You can either say the 4 cancels, or you can say it's 20 over 4, which is 5. Either way you look at it, you get the same result. Does that make sense? All right, so let's see. Maybe we can come up with a general formula. Let's see if we can. Maybe we can think through this. What if we have this? What if I give you x to the nth power? And this time I don't tell you what n is. Just tell you that n is a number. Then can you tell me what the antiderivative of this, and let me put it underneath it. What would the antiderivative of this be? So what do we know about the power? The power on the x. It's got to be one more than whatever's there, right? And then what about out front? Yeah, you don't want this, when it comes out, right, you don't want it to be there. You want it to go away. So I'm going to put 1 over, what? n plus 1. And do you all see that this power would come out, cancel with the n plus 1, then you'd reduce the power by 1 and you'd be here. Do you all see that? And then I say plus c. That right there, everyone, is called the power rule for antiderivatives. So we had a power rule for derivatives, didn't we? The power rule said bring the power out front, subtract 1, right? For antiderivatives, what we say is, okay, add 1 to the power and multiply the front by 1 over that new power. Now, can anybody see where that formula will break down? There is a situation in which that formula will not work. Just look at the formula and tell me what might screw that formula up. If n is -1. What if n is -1? Your formula falls apart, doesn't it? Because then you're going to try and divide by 0. So this formula only works when n is not -1. Any other value of n, this formula works. So what about when n is -1? What's that going to be then? We need to look at that special case. What if n is -1? So let's just write it down. X to the -1, that's what it is, right? That's if n was -1. But isn't that just 1 over x? Remember, properties of exponents, right? Negative, you drop it down. And do you know the antiderivative of that? The antiderivative of that? Natural log, right? We just did this one a second ago, didn't we? Just get used to putting the absolute value around the x when you do the antiderivative. The reason why you have to do the antiderivative is because over here, x can be positive or negative, and it's well defined. But when you do the antiderivative, you can only have a positive number in here, or else natural log's not defined. So, all right, so this formula works for any n except -1, but if n is -1, we have the answer, right? So we've got all bases covered at this point. In terms of powers of x, we're good to go. We have a general formula. So let's do another example. Oh, okay. Now we're starting to get somewhere. So now I've actually given you a function that has 3 terms in it, separated by addition and subtraction. Now, when we were in Cal 1, when we took the derivative, if we had addition and subtraction, we just did them individually, right? Well, good news. It all works the same way going backwards. If you have 3 separate terms, you can find the antiderivative of each one separately. That's great news, right? Okay, so let's try and find it. Let's do these one at a time. What is the antiderivative of x squared? 1/3 x cubed. Okay, yes? All right, let's skip this for a second, because this is the hardest one. How about this one? Negative 4x. What? Where'd you get that from? Well, because we know that the derivative of x is 1, right? So we need to just remember that if we ever see a constant, in Cal 1 we took the derivative of a constant, got 0. But in Cal 2, if you have a constant and you find the antiderivative, it's always the constant with an x attached to it. Right? So the negative 4 becomes negative 4x. I'm also going to have a plus c out here because I'm going to have a whole family of functions, but I still need to work on that root x. So I'll do that on the side here. Square root of x, we all understand, is x to the 1/2 power, isn't it? That's what it means. So this is x to the n. N here for us is a half, right? So can I use my power rule that we just put on the board? Yeah. According to what we said, the antiderivative of this should be 1 over n, which is a half plus 1, right? 1 over n plus 1, x to the n plus 1. Do y'all see the formula? 1 over n plus 1, x to the n plus 1. Any questions on where I got that from? Yes?
So the n is 1/2? Is that what you're saying?
Yes, this right here is x to a power, right? Right? Like that's x squared. So the n is 2. But here, we have to look at root x as being x to a power, which it is 1/2. So this is why in algebra they teach you radical notation, but they also say, hey, rational exponents is better. Because as you progress, you need to always convert your radicals over to powers like this so you can use all the rules. Okay, we have to add fractions. And you know how when you were taking derivatives, you had to get kind of used to subtracting 1? You know, right? When the power would come down, you'd have to subtract 1. You had to kind of get used to that. Well, now you have to get used to adding 1 to these things. So you have to add those together. So, and then you have to add those together. So let's see what we get. 1 over, what's 1/2 plus 1? 3 halves. And then x to the 3 halves. But what does 1 over a fraction become? Just flips it, right? So this is actually just going to be 2/3 x to the 3 halves. Shall we check our work? Take the derivative. Power comes out. What happens when 3 halves hits 2/3? Cancel out. I get a 1. And then I subtract 1 from 3 halves. 3 halves minus 1 is 1/2. And so I get exactly x to the 1/2. So that is my middle piece here. Plus 2/3 x to the 3 halves. I have some good news. In Calculus 2, as you're learning this antiderivative thing, you can always check your answer. When you're taking a quiz or a test and they ask you to find the antiderivative of something, you can always check your work. Just take the derivative of it. When I take derivative of this, I better get this, right? 3 comes out, cancels x squared. Good. 3 halves hits that, gone. Subtract 1 from that. I'm here. Derivative of negative 4x is negative 4. Derivative constant is 0. Boom, I'm there. See? Yeah, it'll get harder later, but I'm just saying you can check your work. Like in theory, you should always be able to check your work. All right.